You see it in the images, and your brain refuses it. A perfect hexagon spinning at Saturn's North Pole. 6 straight edges each, stretching 14,500 kilometers. That is 2,000 kilometers longer than Earth's diameter. The whole structure 30,000 kilometers wide, winds screaming at 320 kilometers per hour. It rotates every 10 hours, 39 minutes, 24 seconds, locked to Saturn's internal rotation rate. November 1980, Voyager 1 passes Saturn at 349,000 kilometers. The cameras catch fragments of the northern hemisphere. Partial views, tantalizing edges of something geometric. Engineers review the data. Something is wrong with the images. Nobody reports a hexagon yet. November 1981. Voyager 2 arrives. More fragments. The viewing angle prevents a complete overhead shot. Scientists piece together the fly by frames. 1988. Astronomer David Godfrey at NASA examines both Voyager datasets. He assembles a mosaic from the 1981 images. There it is. 6 sides, perfect geometry, 78 degrees north latitude, a hexagon that does not shift in longitude like other cloud patterns. It sits there. Stationary relative to the planet's rotation, Godfrey measures the rotation rate against Saturn's radio emissions. They match. The hexagon is anchored to Saturn's interior. He publishes in Icarus. The planetary science community erupts with questions. Nothing like this exists anywhere else in the solar system. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from NASA's Cassini mission archives published through 2025, Harvard University's Department of Earth and Planetary Sciences, peer-reviewed study and proceedings of the National Academy of Sciences from June 2020, and the James Webb Space Telescope observational data presented at the 2025 Europlanet Science Congress in September and Nature. Communications atmospheric analysis from September 2018. Now back to the information. The Cassini team deploys the visual and infrared mapping spectrometer. VIMS detects heat from Saturn's interior radiating upward through the atmosphere. The instrument sees the hexagon glowing in thermal infrared, 75 kilometers deep into the atmosphere. A clearing in the clouds. The hexagon is not a surface feature. It extends down. The measurements show temperature variations. The jet stream defines a boundary. August 2009. Saturn reaches Equinox. The sun crosses directly over the equator. The northern hemisphere tilts into sunlight for the first time in 15 years. The hexagon emerges from shadow. Cassini's visible light cameras lock on. December 10th, 2012. Cassini swings directly over the North Pole. 10 hours of continuous imaging. 8 color-filtered frames assembled into the first complete overhead movie. The resolution is unprecedented. Inside the hexagon, a massive hurricane centers on the pole. The eye alone measures 2,000 kilometers across, 50 times larger than a typical Earth hurricane. Surrounding it are dozens of smaller vortices, reddish ovals. Some spin clockwise. The hexagon and the central hurricane spin counterclockwise. The biggest vortex near the lower right corner of the hexagon spans 3,500 kilometers, twice the size of the largest hurricane ever recorded on Earth. The boundary is sharp. November 2012. Cassini captures the hexagon in natural color, blue-green hues, clear atmosphere. The polar winter between November 1995 and August 2009 cleared the atmosphere of aerosols. Photochemical reactions require sunlight. No sunlight means no haze production. The hexagon acted as a barrier during this period. Particles could not enter from outside. The interior stayed clean. September 2016. Cassini images the same region. The hexagon has turned golden yellow. 4 years of continuous sunlight changed everything. Solar radiation breaks apart methane molecules in the atmosphere. The fragments rearrange into hydrocarbon particles, smog, the same process that creates haze on Earth. The aerosols accumulate inside the hexagon. The color shift documents Saturn's seasonal change. 1 Saturn year equals 29 Earth years. Each season lasts more than 7 Earth years. May 24th, 2017. Saturn's northern summer solstice. The hexagon reaches peak solar exposure. The golden haze intensifies. Cassini's final orbits in 2017 provide the answer. The grand finale, 22 orbits threading between Saturn and its rings. Gravity measurements at unprecedented precision. The high winds measured at cloud tops persist far below, 895 miles per hour at the surface, 1,440 kilometers per hour. These winds extend 5,000 miles down, 8,000 kilometers toward the planet's interior. The hexagon is not shallow. June 2020. Rakesh Yadav and Jeremy Bloxham at Harvard University publish in Proceedings of the National Academy of Sciences. They build a 3-dimensional, fully nonlinear simulation. Deep thermal convection in the outer layers of gas giant planets. The simulation runs for 1 month of computing time. It covers 10% of Saturn's radius. The model spontaneously generates giant polar cyclones, fierce alternating zonal jets, a high latitude eastward jet with a polygonal pattern. The simulation produces a 9-sided polygon, not 6, but the mechanism is clear. Self-organized turbulence in the form of giant vortices pinches the eastward jet. The vortices squeeze the jet stream like rubber bands around a larger rubber band. The compression forces the jet into a polygonal shape. The number of sides depends on the speed differential between the jet and surrounding atmosphere, the size and distribution of the vortices, the depth of the convection. Yadav describes it simply. Imagine placing smaller rubber bands around a central ring and squeezing from the outside. The ring compresses and forms edges. The simulation shows the hexagon likely extends thousands of kilometers deep, much deeper than previous estimates. The Harvard model builds on laboratory experiments. 2010, Ana Claudia Barbosa Aguiar and Peter Reed at Oxford University publish in Icarus. They place a 30-liter cylinder of water on a rotating table. The water represents Saturn's atmosphere. Inside the tank, they place a small ring rotating faster than the cylinder. This creates an artificial jet stream. They track it with green fluorescent dye. The faster the inner ring rotates, the more the jet stream deviates from circular. Small eddies form along the edges. The eddies grow larger and stronger. They force the fluid into polygonal shapes. By varying the rotation speed, they produce triangles, squares, pentagons, hexagons, septagons, octagons. 6 sides appears most frequently. The experiments show that steep velocity gradients between rotating fluids naturally produce polygonal boundaries. The Oxford tank is 60 centimeters wide. The inner circle is 30 centimeters in diameter. The rotation rates reproduce the same relative speed differential as Saturn's polar jet stream. The wave number 6 pattern emerges consistently. The hexagon forms where barotropic instability occurs. The jet becomes unstable and develops meanders and vortices. These settle into a 6-sided configuration. The laboratory results match theoretical predictions. Quasi-geostrophic equations for shallow atmospheric jets favor hexagonal symmetry. The latitude-dependent planetary vorticity gradient on Saturn at 78 degrees north creates the exact conditions. The wave's phase speed matches the background jet speed. The pattern becomes stationary. It does not drift relative to the planet's rotation. Both features align vertically. The discovery suggests the hexagon is a towering structure, hundreds of miles tall. The lower hexagon influences what happens above. The connection between atmospheric layers runs deep. The stratospheric hexagon warms as summer approaches. A high-altitude vortex forms with hexagonal shape. The mystery extends upward. November 29, 2024. The James Webb Space Telescope observes Saturn for 10 continuous hours. The near-infrared spectrograph targets the upper atmosphere. The team comprises 23 scientists from institutions across the UK, US, and France. Professor Tom Stallard at Northumbria University leads the effort. They detect infrared emissions from H3 plus ions, positively charged molecular hydrogen. This molecule plays a key role in Saturn's atmospheric chemistry. The observations reveal unprecedented details. 1,100 kilometers above the 1 bar pressure level in the ionosphere, dark bead-like features appear. They sit embedded within bright auroral halos. The beads remain stable over the 10-hour observation period. They drift slightly, slow dynamics in the charged upper atmosphere. 500 kilometers lower in the stratosphere at 600 kilometers altitude, another structure appears. An asymmetric star-shaped feature extends from the North Pole. 6 arms, but only 4 are visible. 2 are mysteriously missing. A lopsided pattern. The team maps the exact locations. The star's arms emanate from positions directly above the points of the hexagon. The ionospheric beads line up with the strongest star arm. The features span different atmospheric layers but appear connected. A column stretching through Saturn's atmosphere. Stallard states the results came as a complete surprise. They anticipated broad emission bands at various levels. Instead, they found fine scaled patterns of beads and stars separated by huge distances in altitude, yet somehow interconnected and possibly linked to the hexagon deeper in Saturn's clouds. These features are completely unexpected and completely unexplained. The James Webb data suggests processes driving the patterns influence the entire atmospheric column. Simulations show the jet-only system studied in earlier papers does not produce a long-living hexagonal structure. The jet plus North Polar Vortex system does. The vortex stabilizes the hexagon jets against disruption. It suppresses energy cascade to smaller scales. The coupled system maintains the large-scale geometry over extended periods. 2017. A study demonstrates this jet plus vortex configuration produces a long-lived wave number 6 pattern through nonlinear equilibration. The vortex stabilizes the meandering jet. The The hexagon drifts westward at approximately 10 meters per second relative to System 3 coordinates, Saturn's coordinate system based on radio emissions. This drift rate remains constant. Measurements tracking the hexagon over 5.5 years from 2008 to 2014 confirm extreme stability. Despite large radiative forcing in Saturn's atmosphere, the rotation of the hexagon does not change. The structure persists through seasonal transitions. 2022. A mathematical study at California Institute of Technology by Andy Ingersoll and colleagues shows stable geometric arrangements of polygons can occur on any planet when specific conditions exist. A storm surrounded by a ring of winds turning in the opposite direction to the storm itself. Anticyclonic shielding. This creates a vorticity gradient, causing mutual rejection between cyclones, similar to magnetic poles repelling. Storms maintain independence instead of merging. Multiple similar storms space themselves apart evenly. They reject each other equally. Circles self-arrange into hexagons when maintaining equal distance. The theory explains why Jupiter's poles show different patterns. Jupiter has multiple cyclones arranged in circular clusters at both poles. Saturn has one large hexagon. The difference relates to storm size and wind speed. Saturn's polar cyclone is bigger and slower than Jupiter's. It cannot hold a polygonal pattern of circumpolar cyclones like Jupiter. Instead, the side-adjacent vortices and deep barotropic instability create the hexagon. 300 kilometers tall based on Cassini observations, but potentially much deeper based on gravity data and simulations. The jet stream winds reach 320 kilometers per hour. Some measurements suggest wind speeds up to 500 kilometers per hour in certain regions. The rotation period is 10 hours 39 minutes 24 seconds, precisely matching Saturn's radio emission period. This ties the hexagon to the planet's interior rotation. The hexagon sits at latitude 78 degrees north. The structure does not shift longitude. Other cloud features on Saturn drift with varying wind speeds. The hexagon stays fixed. It has existed since at least 1980, when Voyager 1 first imaged fragments of it. 45 years of confirmed observation. Scientists estimate it may have been spinning for centuries. The Oxford laboratory experiments reveal the conditions required. A steep latitudinal gradient in atmospheric wind speed. Rotation differential between inner and outer regions, specific viscosity parameters. The Reynolds number in the experiments ranges from moderate values achievable in the lab. Saturn's Reynolds number exceeds 10 to the 12th power. The Ekman number on Saturn is less than 10 to the negative 14th power. Direct quantitative comparison is impossible, but the experimental Rossby numbers around 0.03 to 0.1 match plausible values for Saturn. The key factor is the relative speed differential, not the absolute speeds. The experiments capture qualitative features: the morphology of the hexagon, the presence of eddies outside the jet, the stability of the pattern, the resistance to disruption. If you value this level of documented research and detailed atmospheric analysis, subscribe to support more content like this. Now back to the final details. Some scientists suggest it relates to seasonal timing when the features were observed. Saturn's axial tilt is 27 degrees. This creates intense seasonal variations. Polar nights last over 7 years, followed by 23 years of variable illumination. The hexagon persisted through these changes. The seasonal variations do not affect it. Both the hexagon and its jet stream are part of an extensive wave deeply rooted in Saturn's atmosphere. The University of the Basque Country researchers studied the hexagon from 2008 to 2014 using ground-based telescopes, PlanetChem and Astrolux instruments at Calar Alto Observatory in Spain. They measured hexagon vertex positions with great precision. The movement remains extremely stable. The jet stream inside stays unchanged. The hexagon represents a manifestation of a Rossby wave, similar to Earth's polar jet stream, which meanders west to east, bringing high and low pressure systems. On Earth, these waves move. On Saturn, the hexagonal wave is stationary. It does not propagate. It sits locked at 78 degrees north, rotating with the planet. The stationary nature requires special conditions. The wave's phase speed must match the background flow speed. Zero relative velocity between the wave and the mean zonal wind. This balance creates a standing wave. Mission planners chose to destroy it rather than risk contaminating potentially habitable moons like Enceladus. The final 22 orbits dove between Saturn and its rings. Gravity measurements during these passes revealed wind structure extending thousands of kilometers deep. The atmosphere of Saturn is not a thin shell. It is an ocean of hydrogen and helium. No solid surface exists. The transition from atmosphere to interior is gradual, increasing pressure and temperature with depth. The hexagon's jet stream taps into this deep reservoir. The Harvard simulation by Yadav and Bloxham models exactly this: deep rotating convection in a spherical shell. 10% of Saturn's radius. Heat from the interior drives convection, like boiling water. Hot fluid rises, cool fluid sinks. Add rotation and the Coriolis effect. The convection organizes into large-scale patterns. Zonal jets form spontaneously. Polar cyclones emerge. The eastward jet at high latitude develops instabilities. Giant vortices form in the turbulent flow. These vortices interact with the jet. They pinch it, compress it, force it into a polygonal shape. The simulation ran for 1 month of computing time. It produced a 9-sided polygon, not a hexagon, but the mechanism is validated. The number of sides depends on parameters: jet speed, vortex size and spacing, rotation rate, convection strength. Fine-tuning could produce 6 sides. The important result is that deep convection alone without external forcing can generate polygonal jets. No need to invoke mysterious mechanisms. The physics is known: fluid dynamics, rotating convection, barotropic and baroclinic instability, self-organization in turbulent systems. The James Webb observations from November 2024 open new questions. The dark beads in the ionosphere, the asymmetric star in the stratosphere, their alignment above the hexagon. Are they causally connected or coincidental? The research team published their findings in Geophysical Research Letters in August 2025. They suggest the beads result from complex interactions between Saturn's magnetosphere and its rotating atmosphere. Energy exchange driving Saturn's aurora. The star pattern indicates previously unknown atmospheric processes in Saturn's stratosphere, possibly linked to the hexagonal storm pattern observed deeper. The ionosphere sits at 1,100 kilometers altitude. The stratosphere at 600 kilometers. The hexagon jet stream at cloud level near 0 altitude relative to the 1 bar pressure surface. 3 distinct layers, 3 different phenomena, spatially correlated, vertically aligned. The simplest explanation is a single physical process spanning all 3 levels, a column of interconnected dynamics. But what process? The answer remains unknown. Saturn's upper atmosphere has proven difficult to study. The emissions are extremely weak. Previous missions and telescopes lacked sensitivity. James Webb changed that. The near-infrared spectrograph detects faint signals. The 10-hour continuous observation on November 29th in 2024 provided temporal coverage. The beads drift slowly. The star rotates with the planet. Future observations are needed. The team hopes for additional James Webb time. They want to track the features over longer periods. Watch them evolve. Measure correlations with the lower hexagon. Determine if the beads and star arms are transient or persistent, whether they change with season, how they respond to auroral activity. No sunlight means no photochemical reactions. Existing aerosols settled out. The hexagon jet stream prevented external particles from entering. The interior became pristine, clear blue when viewed in natural color. After Equinox in August 2009, sunlight returned. Ultraviolet radiation from the sun hits the atmosphere. It breaks molecular bonds. Methane CH4 dissociates. The fragments hydrogen and carbon radicals recombine into larger hydrocarbons. Ethane C2H6, propane C3H8, more complex molecules. These hydrocarbons condense into tiny particles, aerosols, haze. The particles scatter sunlight. Short wavelengths blue scatter more than long wavelengths red. But as particle size increases, scattering becomes less wavelength dependent. The haze appears yellowish, golden. Exactly what Cassini observed. The transition from blue to gold took 4 years, from 2012 to 2016. The haze built up gradually. By summer solstice in May 2017, the golden color dominated. The hexagon jet stream continues to act as a barrier. Particle size distribution differs inside versus outside. Small particles inside, large particles outside. The jet stream segregates them. Differential transport. The boundary remains sharp. This behavior resembles Earth's Antarctic ozone hole. A polar vortex isolates the air mass. Chemical processes inside differ from outside. On Earth, it is ozone depletion. On Saturn, it is haze production. Same principle. Isolated air mass, distinct chemistry. After it emerged from shadow in 2009, ground-based telescopes could see it, even modest-sized instruments. The hexagon is big enough and contrasted enough to detect. The University of the Basque Country team used this. 6 years of ground-based observations from 2008 to 2014. They tracked the hexagon's motion, measured its rotation rate, 10 hours, 39 minutes, 24 seconds. Constant. Unchanging. This matches Saturn's System 3 radio period. Therefore, the hexagon reveals Saturn's true rotation rate, the interior rotation. Saturn is the only planet in the solar system whose rotation period remained uncertain until recently. The planet has no solid surface, no fixed landmarks. The atmosphere rotates at different speeds, at different latitudes. Radio emissions from the magnetosphere provide a clue. The magnetosphere is anchored to the interior. Its rotation reflects the planet's deep rotation. But magnetic field measurements from Voyager showed one period. Cassini measurements showed a slightly different period, 6 minutes slower, which is correct. The hexagon resolves this. Its rotation is locked to the interior. It does not drift in longitude. Therefore, its period of 10 hours, 39 minutes, 24 seconds is Saturn's internal rotation period. Problem solved. The hexagon acts as a clock, a visible marker of the planet's spin. The planetary beta effect. Fluid parcels displaced northward experience increased Coriolis force. Displaced southward, they experience decreased force. This acts as a restoring force. Oscillations develop, Rossby waves. These waves propagate westward relative to the mean flow. But if the mean flow is eastward and fast enough, it can balance the westward wave propagation. The wave becomes stationary in the rotating frame. This requires precise conditions. The dispersion relation for barotropic Rossby waves on a beta plane gives the relationship. Wave frequency equals mean flow velocity times wave number minus beta divided by wave number. For a stationary wave, frequency equals 0. Therefore, mean flow velocity equals beta divided by wave number. At 78 degrees north on Saturn, the planetary beta effect has a specific value. The observed eastward jet speed of approximately 120 meters per second matches the required velocity for wave number 6, a hexagon. The math works. The hexagon is a stationary Rossby wave. Researchers in 1990 suggested this vortex continuously forced the hexagon, perturbed the jet, excited the wave. When Cassini arrived in 2004, that large vortex was gone. The hexagon remained. Therefore, forced wave theory fails. The hexagon is an unforced stationary wave. It arises spontaneously from the jet's instability. Barotropic instability. The jet has a velocity profile with inflection points. The Rayleigh-Kuo criterion for barotropic instability requires the meridional gradient of potential vorticity to change sign. Saturn's polar jet satisfies this. The jet is unstable. Perturbations grow. They organize into waves. The wave number that grows fastest depends on jet width and speed. For Saturn's north polar jet wave number 6 dominates, a hexagon. The instability saturates nonlinearly. The wave amplitude reaches equilibrium. Energy input from the mean flow balances dissipation. The hexagon persists, stable, unchanging. 45 years and counting. The simulation used a rotating spherical shell. Inner radius 7/10 of outer radius. Rotation rate chosen for computational efficiency. Temperature contrast across the shell drives convection. The Rayleigh number controls convection vigor. The Ekman number controls viscous effects. The Rossby number controls rotation effects. Adjusting these parameters changes the outcome. Different jet speeds, different vortex sizes, different wave numbers. The simulation proves the concept. Deep convection can produce polygonal jets. Achieving exactly wave number 6 requires parameter tuning. Future simulations will refine this. More computing power, higher resolution, longer runtimes, better matched to Saturn's actual conditions. The goal is a simulation that spontaneously produces a hexagon, not a 9-sided polygon. Then the theory is complete. Why does Saturn have a hexagon and other planets do not? Jupiter has circular polar cyclones. Multiple storms arranged in clusters, 5 around the North Pole, 5 around the South Pole, no polygons. Uranus and Neptune show complex polar dynamics, but no hexagons. Earth's polar vortices are roughly circular, sometimes elongated, never hexagonal. Mars' polar vortices are circular. Venus has a double vortex at the South Pole, 2 eyes, but not hexagonal. Saturn is unique. The answer may lie in the specific combination of conditions. Saturn's rotation rate, 10 hours 39 minutes, fast, its size, 58,200 kilometers equatorial diameter. Large, its atmospheric composition, 96% hydrogen, 3% helium, trace methane, ammonia, ethane, no solid surface, deep atmosphere, thousands of kilometers, strong zonal jets. Wind speeds up to 1,800 kilometers per hour at the equator. These factors combine, they create the right environment, the right instability conditions, the right balance between jet speed and planetary vorticity gradient. The hexagon forms, it stabilizes, it persists. Change any one factor and maybe you get a different result. Jupiter is bigger, rotates faster, different composition ratio. Its polar jets behave differently. Multiple cyclones form instead of one hexagon. Saturn sits in a sweet spot, the Goldilocks zone for hexagonal jets. 294 orbits, 635 gigabytes of data, 453,000 images. The legacy includes the hexagon, mapped in visible light, infrared, ultraviolet, tracked through seasonal changes, color shifts documented, vertical extent measured, wind speeds determined, gravity measurements probed deep structure, The hexagon is now understood. Not completely, but far better than 1988 when Godfrey first published the discovery. We know its size, its rotation rate, its stability, its depth. We have laboratory experiments reproducing polygonal jets, computer simulations showing spontaneous formation, theoretical frameworks explaining stationary Rossby waves, observational data from multiple missions spanning decades. The hexagon is real. It is documented. It is not an artifact. It is a natural consequence of fluid dynamics on a rapidly rotating gas giant planet with specific atmospheric conditions. James Webb probes its upper reaches. Future missions may go deeper, atmospheric probes descending into Saturn's clouds, measuring temperature pressure composition, wind speed all the way down, tracking how the hexagon changes with depth, whether it remains six-sided or evolves into a different structure, whether the jet stream extends to the interior or terminates at some level. These questions await answers. For now, the hexagon spins. 320 kilometers per hour winds, 10 hours 39 minutes, 24 seconds rotation, 14,500 kilometer sides, 30,000 kilometers wide, 180 kilometers tall, maybe thousands of kilometers deep, 45 years observed, possibly centuries old, a geometric storm on an alien world, perfect six-sided symmetry in a chaotic atmosphere, nature organizing itself, turbulence creating order. The hexagon exists because physics demands it. Rotation, convection, instability, self-organization. These forces shape Saturn's atmosphere. The hexagon is their signature. Reduced emission from H3 plus ions and methane fluorescence. The beads drift slowly over the 10-hour observation. Motion tracked. Positions mapped. The stratospheric star below them has 4 visible arms, 2 missing. Why? Asymmetry suggests ongoing dynamic processes, not a steady state. Something disrupts the symmetry. Magnetic field interactions, atmospheric waves propagating upward from below, auroral precipitation patterns. The team notes the darkest ionospheric beads align with the strongest stratospheric star arm. Correlation. But correlation does not prove causation. The features may be linked, or the alignment may be coincidence. More data needed. The paper, in Geophysical Research Letters, published August 2025, presents the observations. It stops short of definitive explanations. The phenomena are completely unexpected, completely unexplained. The words echo, science confronting mystery. The hexagon opened the door. Now we find rooms beyond. Each observation reveals more complexity, more structure, more questions. Saturn's atmosphere is not a uniform gas ball. It is layered, stratified, organized, interconnected. From cloud tops to ionosphere, the hexagon may be the visible tip of a vast atmospheric column, a chimney running through multiple layers. Energy flows up and down. Particles transported, momentum exchanged. The full picture remains incomplete. A storm that does not know it is special. It simply exists, governed by physics, shaped by forces beyond human control. We study it because it fascinates us, because it reveals how nature works, because it shows us that even in chaos there is order. Even in randomness there are patterns. The hexagon is a message written in wind and cloud. We are learning to read it, slowly, line by line, frame by frame, observation by observation. The message says this: the universe organizes itself. Given the right conditions, structures emerge, patterns form, hexagons spin for centuries, and humans, 7,500 light minutes away, look up and wonder. That wonder drives science. That curiosity builds spacecraft. That need to understand sends probes across the solar system, to Saturn, to the hexagon, to measure and document and calculate and simulate until we grasp what we see. The hexagon is strange, but the reason it exists is physics, plain and simple. Rotation plus convection plus instability equals hexagon. On Saturn. At this time, for as long as the conditions persist. The same pattern Saturn displays across 30,000 kilometers. Scale does not matter. Physics scales. The ratio of forces, rotation to viscosity, inertia to pressure gradient. These dimensionless numbers govern behavior. Match the numbers. Get the same pattern. A hexagon in a tank. A hexagon on a planet. The universe repeats itself. Different sizes, same rules. This is why laboratory experiments work. This is why simulations succeed. The equations are universal. They describe water. They describe hydrogen. They describe atmospheres on Earth or Saturn or exoplanets around distant stars. Find a fast rotating gas giant. Strong zonal jets. Right temperature profile. You will likely find polygonal storms, maybe hexagons, maybe pentagons or septagons. The number of sides is a detail. The existence of geometry is inevitable. Fluid dynamics demands it. Instability creates it. Nature selects the configuration that fits the constraints. On Saturn, it chose 6. Vortices spinning, final orbits, gravity deep winds, the grand finale. 13 years compressed into terabytes of data, researchers analyzing, publishing papers, PhD theses written, careers built, studying one storm, one jet stream, one hexagon. James Webb follows. 10 hours in November 2024. Beads and stars, new layers revealed, new questions posed. This is science, incremental, methodical, building knowledge frame by frame. Observation to hypothesis, hypothesis to test, test to theory, theory to prediction, prediction to observation. The cycle continues. The hexagon provides endless material. Every measurement refines understanding. Every simulation adds nuance. Every laboratory experiment confirms principles. We know more now than we did in 1988. We will know more in 2035. The hexagon is patient. It spins and waits. We catch up slowly. On Earth, weather is solar-powered. Sunlight heats the surface. Warm air rises. Circulation begins. On Saturn, internal heat dominates. The atmosphere churns from below. Convection cells form. Rotation organizes them. Zonal jets emerge. Eastward and westward, bands circling the planet. At high latitude near the pole, one particular jet. Eastward, fast, 120 meters per second, 320 kilometers per hour. Barotropically unstable. The instability grows. Meanders develop. 6 lobes. Vortices form between the lobes. They pinch the jet. Lock it into hexagonal geometry. The pattern stabilizes. 45 years minimum. Possibly centuries. As long as internal heat keeps rising. As long as rotation continues. As long as the jet persists. The hexagon spins. The reason Saturn's hexagon exists is rotation plus convection plus instability. 3 ingredients. Combined, they produce 6-sided geometry. Not magic, not mystery. Physics, documented physics, measured, simulated, replicated in laboratories, published in peer-reviewed journals, NASA mission data, Harvard computer models, Oxford experimental tanks, James Webb infrared spectroscopy, 45 years of investigation. The hexagon is understood. Not completely. Details remain. The beads and stars above, the precise depth below, the exact conditions selecting wave number 6. But the core mechanism is clear. The hexagon exists because on Saturn at 78 degrees north, the atmosphere is organized by forces that favor 6-sided patterns. It is as much a consequence of natural law as water flowing downhill or planets orbiting the sun. Inevitable, given the conditions. Strange to human eyes, normal to physics. The hexagon is not an anomaly, it is a solution. Nature solving an equation. The equation has constants, rotation rate, planet size, atmospheric composition, temperature gradient, jet speed. Plug in Saturn's values. The equation outputs 6, a hexagon, spinning, stable, documented, real.